It's the same chemical formula. I'll work with the C5H12. Notice 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5, 6, 12 hydrogens. That's the same formula. That's an isomer. Okay? Because isomers, there's the iso, it has the same formula, different structures. So I'm going to talk about different ways of naming these isomers, and they're all due to differences in the structure, so you can call it in general a structural isomer, but there are specific names also. Now here, no matter how I do it, the longest carbon chain is 3. It's saturated, there's my A and E. What do I do with these things? Well, if I were a real organic chemist would say something like neopentane. And I say, what the heck is neopentane? It's a common name for that molecule. First of all, I never want to see common names. I might give you a common name and expect a structure because I make jokes about the common name system. But I always want to see IUPAC names. That means these things are called substituents. We replaced carbon, or we replaced the hydrogen that was originally there with a carbon. And when we have substituents with the carbon, it's the number of carbons, so that's meth, with the word ending YL. If it's 2 carbons as a substituent, then it would be ETHYL. So there are 2 methyls. So it's dimethylpropane. And then sometimes you have to use numbers to locate it, but there's no other place I can put 2 methyls on the propane basic structure there, the propane basic chain. This is called the backbone of the molecule. So when I change the backbone, as a 3 carbon, and you do this, and these say that you have these 2 carbons coming off. That's why I don't like that, because you say, how do I know they're not hydrogens? Because you don't draw hydrogens into this structure. That's how. Compared to 1, 2, 3, 4, 5. So here the carbon chain, the backbone went like this. Here it went like that. So this is sometimes referred to as backbone in the old days, or skeletal isomerism. They're different structures. But the key you use to determine that, here we have dimethylpropane. Over there we had pentane, wherever I wrote it. Did I write it anywhere? I guess I wrote pent, but I didn't put an ending. So the other one was pentane. Okay. Next thing we can do, of course, is there another isomer? And the answer is yes. Because again, if I put in my hydrogens, this is sometimes why I ask you to do that. Notice again, I have 5 carbons, 12 hydrogens. Here, the longest carbon chain is BUT, so it's a butane. So the way you recognize skeletal isomers is the backbone, or the main structure of the carbon is changed. You have a different numerical prefix. And again, there's a substituent, a methyl group. And you always look for, when you're naming this, longest carbon chain. And to confuse you, I can bend it around like this, but if you go like this, you found a long carbon chain of 5. As you go from one carbon to the next without picking up your pencil, you keep doing it until you get the longest carbon chain. You can't jump over things and you can't backtrack or anything else like that. Then somebody said, should I call that 2-methylbutane? On 1,2 carbon? And the answer is no, because if I put it over here, it's still what?
Same thing.
Same thing, so the 2 is redundant. And the other thing, somebody says, how about 1-methylbutane? Anytime it's 1-methyl, it means you didn't find the longest carbon chain. That's the longest carbon chain. Is a 5-carbon chain. So anytime you find yourself saying 1 something or other with a carbon substituent like this, it means you didn't find the longest carbon chain. And the basis for nomenclature is always the longest carbon chain. Now other things, which I'm not going to ask you about, but organic chemists refer to these as alkanes. They also refer to them as paraffins. Wax is where paraffin came from, I guess. And if you have 20, 30 carbons in a chain, it's a waxy molecule, paraffin, or wax, whatever you want to call it. So I just toss that in there because organic chemists have a lot of different ways to refer to the same thing. Okay. The most confusing is the common system nomenclature. And I always like to point out, in the old days of chemistry, we had alchemists, and each alchemist had, or each group of alchemists, because they were groups, each group of alchemists had their own symbols for the different elements. So one group would have one symbol for carbon, another group would have a different symbol for carbon. And the whole reason they did that, if they ever figured out how to make gold out of the base metals, in other words, non-gold things, they'd be rich. And if everybody knew how to do it, everybody would be rich and gold would be worthless. So they wanted to keep secret what they were doing. They had to communicate with themselves, but they didn't want anybody else to know in case they figured out how to make gold. Yes?
Where's the M and the N stand for?
The what?
The M and the N stand for what?
Where are we?
The formula.
A.
It's CN2N.
Oh, this is any number. 1 carbon, right? This would be 2 plus 2 is 4, CH4, methane. 2 carbons, then it would be C2H6.
He can't see that those are both N.
Oh. Oh.
It looks like an
things
N.
don't look right. Oh, okay, well, let me write it better. Oh, it's just the way of figuring out how many carbons and hydrogens there. If you see a molecule and you have 2 times the number of carbons plus 2, then you know it must be saturated and it's an alkene. And they call that I, because they all fit that formula, I guess. No, I can't keep them right. Here, this is an H.
And N is the subscript to C.
It's a homologous series. They all have the same formula. Okay. I don't know why they do this. They just do things like that in organic chemistry. But they quickly get away from that. They start getting more complex. Anyhow, getting back to my story of alchemists, organic chemists are a modern version of alchemists. The reason they have the common system of nomenclature if you ever find the drug that cures cancer, and everybody knows what you're talking about before you can patent it and start making a fortune selling it, you're not gonna get rich. So they all talk in all these common systems of nomenclature, and if you're not with that group, you don't know what they're talking about, okay? I remember my first seminar in graduate school, we had this English chemist up there, and he kept saying the methyl this and the methyl that, and I kept saying, wow, that's a really amazing thing. Guess what he's talking about? This. I've been used to hearing methyl in all my 4 years of organic chemistry and things, and this English chemist came in and started talking about methyl because they pronounced the word differently. I thought he had some new remarkable compound until he started drawing formulas on the board. Okay? So you have to be aware of that. There's different accents, and when you can't read my writing, it's as though we're talking a strange language. So that's what organic chemistry is, a strange language. Okay, so these are the alkanes, the hydrocarbons. Well, we're going to deal with hydrocarbons, and I'll start putting oxygens into the molecule soon. What else can I do with alkanes? I've just about beaten it to death, right? I can't think of anything else at the minute. So I'm going to do a chemical reaction. I'm going to break this bond right here. This is what organic chemists do. And I'm going to make hydrogen. And these two electrons go in here, and I make this, a double bond. Has a fancy name. I dehydrogenated. I removed hydrogen. Okay. And whenever you have a double bond, these are referred to as alkenes. And there's the word ending E-N-E. That's going to identify alkenes. Okay. And I can even do this thing. Because I took away two hydrogens, so it's CnH2n. What are we looking for?
Oh, it's the glare.
Oh, it's the glare. What can I do about that? Not much. Oh, I know. I can turn off my projector. I don't need the projector. Oh, but there is an alkene down here. Somebody asked me right here. So, come back to that. Is that better? Okay, so there's the first member. And for an alkene, you can't have less than one carbon. So you can't put one here and then have H2, so that won't work. Because carbon always wants to have 4 bonds in organic chemistry. They can be double bonds, as in this case. Notice 1, 2, 3, 4 bonds for this carbon. 1, 2, 3, 4. We can do the electron dot structures. We did that already. Been there, done that. So these are alkenes. They're also referred to as unsaturated molecules. And when you buy your unsaturated margins, it means somebody took the cheap margin, I guess, and took away some hydrogens and sold the hydrogens separately and raised the price of your margin. Now you get the unsaturated ones. They're polyunsaturated. It means it has many double bonds. Oh, how about that? All marketing. Okay, what can we do with alkenes? We can do a lot of things with alkenes. First of all, I mentioned up here for the 4 separate bonds, it was an sp3 hybrid. When we start doing this, this is an sp2 hybrid. Now there's my double bond, and I'm putting something like this I'll do my fancy picture over in the other room, I guess, but I'll put something like that. But one of the things you'll notice, before I said there is free rotation about the single bond, this thing's merrily spinning away. The higher the temperature, the faster it's spinning, and the more complex the motions of those things. Here, the double bond keeps it locked in a position. So there's no free rotation about a double bond. The sp2, this bond is made up of a sigma and a pi molecular orbital. Okay. So those are terms for the double bond. It has a double bond, we call it unsaturated. And the other term you see, and again, I don't know where this came from, but organic chemists, I don't know if Dr. Jones used this, maybe only old organic chemists used to do it, but Easy Ed always talked about paraffins and olefins and all sorts of things. And we were even close to the ocean. Okay, back to this thing then. These are the alkenes, and I'll talk about that in the other room.